Now, due to my misguided thinking, again, thinking I'd made a mistake when I hadn't, which means I'd made a mistake in thinking that I'd made a mistake, we didn't get as much time as I'd like to talk about the differential. But I did write down the definition of the differential. I think I wrote down the definition of the differential someplace. I wrote it down here. I wrote all this. And then I came up here. Okay, I wasn't sure where I was. Okay, the differential we call df, and it's a partial with respect to x. It's partial of f with respect to x plus times delta x plus the partial of f with respect to y delta y, which we write as fx delta x, fy delta y. This is the more compact notation, but it means exactly the same thing. And of course, the differential would be a function of x and y. So I don't have df of xy and df of xy, partial of f of xy with respect to x and stuff, but that's understood. Okay, now, for given xy, and we could call it an x naught y, not just the same thing we would have over here, the rate of change of f with respect to x is just your fx, and we know that already, we saw that. The rate of change of f with respect to y is just fy. And if we multiply fx by delta x, the rate of change of f with respect to x times how far we move in the x direction gives us the change in z, the change in the value of the function as we move in the x direction. Now, there's a little bit of a hand-waving explanation, but you can write down the limit definitions and everything. It all works out. Try to give you a feel for this. Okay, then the meaning of this is the rate of change of f with respect to y. So that means what? The rate at which f changes if y changes. Okay? If we multiply that by the change in y, we should get, again, the change in the value of the f function, this value of z. So if we move a little bit in the x direction, we get this change, and then we move a little bit in the y direction, we get this change. We add these up and we get the total change in the value of the function. And that's the df. Now this is the approximate change in f when x changes by delta x and y changes by delta y. Now we're going to use this function as an example, since we've just got done analyzing it and finally got the tangent plane interpretation straight. F of xy is this, so we know what the partials are, so I just write this out. Fx delta x is just 2xy minus y squared, because that's fx, times delta x, and then our fy here times delta y. Then I say, okay, what is df if x changes from 1 to 1.1 and y changes from 1 to 0.9? Now, we just figured out what the tangent plane does, what the value of the tangent plane is, and the value of the tangent plane and the change in the value of the function is 0.2. Okay, that's what we got from the tangent plane. Now let's see what we get over here. Okay, so df is, well, we evaluate this derivative, partial df sub x, derivative of f with respect to x, at 1, because x changes from 1 to 1.1, y changes from 1 to 9. So this means that our, it's as though we're starting at 1, 1, and x changes to 1.1, so changes by 0.1. And y changes from 1 to 0.9, so changes by negative 0.1. Okay, so the value of the function at 1, 1, our starting point for these changes is, the value of the x derivative is 1. And of course, that's the same value we use in getting the tangent plane. And we multiply that by 0.1. And then our y derivative we evaluate this is going to give us negative 0.1. We evaluate it again at the 0.11, and we use a change in y of negative 0.11. So if we start at 1, 1, move a tenth of a unit in the x direction, move a tenth of a unit in the negative y direction, this should be the change in our value of the function. And we work that out, and lo and behold, we get 0.2, which is the same change we would get from the tangent line, because the differential and the tangent plane, the differential and the tangent plane give us exactly the same result. So differential is, in a sense, just another linear approximation, a tangent plane approximation. I say linear because a tangent plane is a straight line in any direction, okay? Of course, the slope of the line changes and all that stuff, and I'll make that more explicit later. So 0.2 is your df, that's the approximate change in the function. And your delta f is 0.198. The 0.198 you get if you actually evaluate this. Remember that we started at the 0.11 where z was 0, right? So the tangent plane predicts that if we go from 1,1 to 1.1.9, our z value will go from 0 to 0.2. That's a change of 0.2. This tells us that if we actually evaluate the function at this point, we went from z equals 0 here to z equals 0.198 here. Here we don't see what the original value of the function was, okay? And usually the function will not start at value 0. But the change in the function will be equal to whatever the differential tells us. So it's kind of a little unfortunate that I chose points and a function. Of course, z was 0 because there's something a little misleading in this, but we'll try to patch that up in our next class. Okay, again, takeaway, here's how we do the differential. It tells us the change in the function. Here we have the tangent plane, and the values on the tangent plane were approximate values of the function. Now, those values are approximate values of the change in the function also, since the function was originally 0. But the function isn't always originally 0 again. Okay, take it from there.